So just remember, when we were looking at special univariate distributions, we looked at special discrete distributions, and we also looked at special continuous distributions. And the last continuous distribution that we looked at was the normal distribution. The normal distribution. And I said that it is bell-shaped. It has the shape of a bell. And I said that we will say more about it. I said that we will say more about it. For the other distributions, we had seen how to apply them, but we did not do this for the normal distribution. So today I would like us to look at how we apply this distribution. Now, when we have the normal distribution, I said that generally in life, we may have some data, or we may consider an occurrence where an occurrence for which we have some special interest. Let's say we were looking at the weights of some young people, and let's say that the mean weight is 60 kilograms. So obviously, there are a few young people who may be having a weight higher than 60 kilograms. And there could be a few people who have a weight lower than 60 kilograms. And maybe we want to find the probability that some of the young people have a weight ranging between, let us say, 55 kilograms and 65 kilograms. We want to find the probability that some of the young people having a weight between 55 and 65 kilograms. So first and foremost, we need to note that when we get data from a naturally occurring scenario, most of the time we find that the data is normally distributed, where most of the data values tend to cluster around the mean. We may have a special interest for finding the probability that some people weigh between 55 kilograms. We may be interested in finding out the probability of having some weighing between 55 and 65 kilograms. Or for instance, even right now, the emerging issue about this COVID-19, maybe if there was a hypothesis that maybe most of the people affected are 65 years of age, then maybe someone wants to know the probability that people between 60 and 70 may be affected. Okay. Now, what happens? This happens to the weight. If we are talking about the age of people, maybe 65 years, maybe the mean age of the persons who are highly affected, maybe 65 years. So maybe we want to find the probability that people between 60 and 70 are affected. Or let us say that we are measuring the length of a particular leaf from a particular tree, and maybe we want the probability that the length will lie between 2 centimeters and 4 centimeters. Now you can see all this data is normally distributed, but the mean value differ. The mean values differ. One of them is 60 kilograms, another one 65 years, another one 3 centimeters. So this requires us to standardize. It requires for us to make statistical inference, we need to use the standard normal distribution. We need to use the standard normal distribution. And let me just show this standard normal distribution. So I'm opening a slide. And now I'm sharing my screen. I give it 1 second so that everybody can see this slide that I've just opened. So what I'm presenting here is the standard normal distribution. It is normally distributed with mean 0 and variance 1. You can see the mean here. The mean is 0. To the right of 0, there are some positive values. To the left, there are some negative values. So from 0, right, moving towards the right, we have 1, 2, and 3. So this 1, 2, and 3, they represent the standard deviations away from the mean. Remember, we have been talking about variance, and we've been talking about standard deviations. So 1, 2, and 3 are standard deviations, positive standard deviations away from the mean, and -1, -2, -3 are negative standard deviations away from the mean. Now, if we go back to my whiteboard, you can see that, and maybe I just give it a second so that everybody can see the whiteboard. So you can see here we have 60 kilograms, 65 years, and 3 centimeters. What we usually do is we standardize. We standardize. We standardize. Let me just write here at the top, application of the normal distribution. Application. So what we usually do is to standardize. What do I mean by this? When we standardize, we usually get this value, which we call the z-score value, which is obtained by considering the random variable minus mu over sigma. When we do this, we are actually standardizing, because we use the same table we end up using the same table to perform different calculations, for data which do not have the same units. So when we standardize, we take a random variable, subtract the mean, and divide by sigma. Then we end up with the table, then the standard normal, which I am now displaying. We end up with this standard normal. For any data set, if we subtract the mean, for example, in the first case, it was 60 kilograms. So it will be x minus 60 kilograms divided by the standard deviation for the kilograms. We will end up with, if we consider that from for all the values of x, then we will end up with -3, -2, -1, 0, 1, 2, 3. If we consider this length of 3 centimeters, and then we take any of the random variables x minus 3 divided by the standard deviation, we will end up with the standard normal distribution. Let me display it again. The standard normal distribution. So why do we do this? We usually standardize so that we end up with the standard normal distribution because we want to use that standard normal distribution to perform for our calculations. Now, let us look at an example so that we see how we apply the normal distribution. Application of the normal distribution. So let's look at an example so that we see how we apply this normal distribution, and especially after we have standardized it. Or we find ourselves in situations where we are given a question and then we standardize depending on the question, and then we end up using the standard normal distribution. Okay, example. Suppose the measurements of 800 items are, suppose the measurements of 800 items are normally distributed with mean 66 centimeters, and standard deviation 5 centimeters. I will repeat that. Suppose the measurements of 800 items are normally distributed with mean 66 centimeters and standard deviation 5 centimeters. Find the number of products. Part 1, between 65 and 70 centimeters. Between 65 and 70 centimeters. Part 2, greater than 72 centimeters. Greater than or equal to, greater than or equal to 72 centimeters. Okay, so in this question, there are 800 items. Which are normally distributed. They are normally distributed with mean 66 and variance 25. Why am I saying the variance is 25? Because we are given the standard deviation as 5. We are given the standard deviation as 5. So the variance is 25. Find the number of products with measurements between 65 and 70. We want to find the probability that X will lie between 65 and 70. So that is X less or equal to 70, greater or equal to 65. Greater or equal to 65. So if we, let's just have try to understand this better by looking at a normal distribution. So we are saying that there are some products here, let's say 70 on the upper level and 65. Now we need the probability, we need the number of products with measurements between 65 and 70. Once we get the probability, we can multiply that probability by 800 to give us the number of products. So first and foremost, we need to get that probability. We need to get this probability. And we've been told in that question that the mean is 66. The mean is 66. So for us to get this probability in the shaded region, we can get the probability that X is less than 70, and we subtract the probability that X is less than 65. So I'm saying that from this expression, probability that X is less or equal to 70, greater or equal to 65, this expression is the same as we are looking at for the probability that X is less or equal to 70 minus probability X less or equal to 65. So you can see I'm using less or equal to 65 interchangeably because for the continuous normal, we cannot get the probability of X being equal to 65 as a single item. So now we need to standardize in order for us to use the standard normal distribution. So this will be the probability that the z-score value, this value which I am calling z-score value, the one I am underlining in red, it is the same as the same one which I wrote when I said that we need to standardize. So this z value, it is known as the z-score value. and it is the one that we shall read from the standard normal distribution. So when we are standardizing, we are actually looking for the z-score value. So what is the process of standardizing? We take the random variable x, which is 70, minus mu. The mean is 66. Divide by sigma. Sigma was already given. It was 5. Minus probability that the z-score value, how do we get this z-score value here? Where we have x less or equal to 65, x minus mu over sigma gives us the z-score value less or equal to, now let us standardize 65 minus 66 over 5. So this will be probability that the z-score value is less or equal to 70 minus 66 over 5 is 0.8. Then minus probability that the z-score value is less or equal to minus something minus 0.2. I can see my network is showing me a red signal. I hope I will still be audible. If I'm not audible, the class rep will call me. The red signal has gone. Okay, so how do we read this from the tables? I had given you some tables. Let me share mine. I gave you also the standard normal. Documents. It's still opening. Okay, let me share my screen. So you have your tables too. Now I'm looking at the standard normal. So look at that curve at the bottom. It is the standard normal distribution, and you can see the shaded area. The shaded area is the one represented by the numbers within the table. Within the table, at the top, we have x 0, 1, 2, 3, up to 9. On the left side, we have 0.0, 0.1, up to 3.0. So how are we going to use this table to answer the question that was asked? If I can go back to my whiteboard, we can see that we need the probability that the z-score value is less or equal to 0.8 minus probability that the z-score value is less or equal to minus 0.2. Okay, so first of all, let's look for z-score value less or equal to 0.8. So going back to the table, at the top left, we have x. The values below it, which are 0.0, 0.1, up to 3.0, these are the z-score values. Now, for a z-score value of less or equal to 0.8, if we look at 0.8, just in the normal manner that we usually look at log tables, look at 0.8 from the left and move towards the right, you will see 0.788. At the top of 0.788, there is 0. So the z-score value 0.8, which is the same as 0.80, gives us a probability of 0.788. How do we interpret that? Let me show that on the whiteboard. It means that if this is our standard normal, then, of course, for the standard normal, the mean is 0. So at this point where there is 0.8, it is positive, so it's to the right of 0. So from minus infinity up to 0.8, the whole of this area, is 0.788. This area has a value of 0.788. So this will be equal to 0.788 minus another quantity minus, now let's look at probability that the z-score value is less or equal to minus 0.2. If I can explain that using the standard normal, which is symmetrical at 0, there is a value here which is 0.2, and there is a value on the left which is minus 0.2. So we need the area which is shaded in red, because that area is the one which has a z-score value of minus 0.2. How do we get that area? Now, this area to the left of minus 0.2, it is the same as 1 minus, the area. You see, if I can rephrase that sentence, the shaded area to the left, which is shaded in red, is the same as the area shaded in black on the right. Since our table has positive values, then we need to find the area shaded in red, but it is the same as the area shaded in black. And we can get this area shaded in black. How do we do that? We know that the area under the curve should be 1. So it will be 1 minus the area from minus infinity up to 0.2. To get, I'm repeating, to get the black shaded area, it is the same as 1 minus the area from minus infinity up to 0.2. So how do we know the value of the area from minus infinity up to 0.2? We go to our standard normal tables. Under X, there is 0.0, 0.1, 0.2. 0.2, moving to the right, I have 0.579. 0.579. I go back to the whiteboard, so it is minus 0.579. So we have used what we know to get what we do not know. So what we are actually saying is that so the black area is 0.421. That black area. And how did we get it? 1 minus the z-score value at 0.2. And this 0.421 is the same area as the red shaded area. So because the standard normal is symmetrical, we found the black shaded area, which is the same as the red shaded area. And if we perform this subtraction, we will find that our answer equals 0.367. 0.367. So actually, now we have found the probability that the items lie between 65 and 70. We have found this probability, the one which I'm now shading in red. We have found that probability. That probability is 0.367. So now we can easily tell the number of items which have a length between 65 and 70. How do we do that? We just multiply 800 by 0.367. And the answer is 293.6. 293.6, which we just approximate to 294. We approximate it to 294. So we have answered the first part of the question. What is the second part asking for? Find the number of products with measurements greater than or equal to 72. Greater than or equal to 72. So we need probability that X is greater or equal to 72. Now, you will agree with me. Okay, let's just go to our normal. We try to visualize where 72 could be lying. So 72 maybe is somewhere here. 72 could be, it is just next to 70. So now we want the probability that X is greater or equal to 72. Probability that X is greater or equal to 72. So you'll agree with me that that probability is the same as 1 minus probability that X is less than 72. And so this is the same as 1 minus, and then again we standardize 1 minus probability that the z-score value is less Then 72 minus what is the mean? 72 minus 66 divide by 5. And this is the same as 1 minus probability that the z-score value is less than what? 1.2. 1.2. And so now we have some knowledge of reading from the standard normal distribution. So this is equal to 1 minus z-score value less than 1.2. So we go to our standard normal z-score value, 1.2. I can see 0.885. So it is 1 minus 0.885. And this gives us an answer of 0.115. And then when we multiply 0.115 by 800, then now we can answer the question. And then our answer should be that 92 items have a measurement greater than or equal to 72. So we multiply 0.115 by 800, which gives us 92 items. So that is how we usually apply the standard normal distribution. We apply the normal distribution, and when we standardize, then we end up using the standard normal distribution. I think I will give a question to the class reps, for your practice. Now, let us continue to the main topic for today. I would like to talk about our main topic today is probability distributions used for statistical inference. Our main topic for today is probability distributions used for statistical inference. So, definition, what is inferential statistics? Inferential statistics. I've said that we want to look at probability distributions which are used for inferential statistics. So the question is this: what is inferential statistics? And why should this question be important? It's because we have looked at special univariate distributions. We have described some distributions which are used more frequently in life. Now we want to look at a few distributions which are used for inferential statistics. So definition: inferential statistics involves estimating. Inferential statistics involves estimating population parameters. It involves estimating population parameters from sample statistics. We usually have two branches of statistics: descriptive statistics and inferential statistics. Descriptive statistics involves the mean, mode, median. Now, for inferential statistics, what we usually do is we usually do a few we do a few calculations to ascertain whether a particular value really represents the population parameter. Okay, so we are going to look at 4 probability distributions, and the first one is the standard normal distribution. Standard normal distribution, the one that we have just been talking about. Standard normal distribution. Standard normal distribution. So I will just display it again. So that is the standard normal distribution. You can make a note of it, how it looks like. It has a mean of 0, and it shows us the standard deviations away from the mean. Oh, my network is bad. I can hear. Am I still audible? If I'm audible, please say hi. My network wants to misbehave. I think I must be audible because I've seen, yeah, thank you, Njoroge. Thank you, Cherono, Justin. Thank you, Martha. Okay, let's continue. Thank you. Right. And thank you, Wamono, Madiba. That Madiba sounds like Mandela. Thank you, Ken. Okay, let's continue. Thank you for the highs. So I was displaying the standard normal distribution, the standard normal distribution, and I was saying that it has a mean of 0, and it has 1, 2, 3, and negative 1, 2, 3 standard deviations away from the mean. And you can see at the top right, I have shown that it is normally distributed with mean 0 and variance 1. It is usually normally distributed with mean 0 and variance 1. And then at the bottom, I have given the PDF of the standard normal. The PDF of the standard normal. But for us, we are just interested in understanding these values from -3 up to 3. These are the z-score values. These are the z-score values. When we standardize, we end up with the z-score values. Once we have got our z-score values, we go to the tables for the standard normal distribution, and we read the relevant probability. Now, I have said that our major topic now is probability distributions used for inferential statistics. And I've said that the first distribution we're looking at is the standard normal distribution. Let us just note down the circumstances under which we usually make use of the standard normal distribution for inferential statistics. When we want to perform inferential statistics, when do we use the standard normal distribution? So we can just write that the standard normal distribution is used in performing inferences. It's used in performing inferences for a population mean, when the population when the population being sampled is normally distributed, and the population variance is known, and the population variance is known. I'll just repeat that. It's used in performing inferences for a population mean when the population being sampled is normally distributed and the population variance is known. Okay, let's just mention two important properties that that help us. And of course, I think you already know the properties because we've just used the standard normal. Anyway, the first property, the total area is equal to 1. The total area is equal to 1. And secondly, it is symmetric about 0. It is symmetric or symmetrical about 0. So those are important properties. Now, let us just do a small practice. A small practice here. Now I'm on the whiteboard. We want to do a small practice. We want to be able to get particular areas. Okay, we will do it in the form of an example. Example, find the area to the left of, or find the area to the left of z-score value 1.23. 1.23. We just want to learn how to be able to read some of these values. Find the area to the left of z-score value 1.23. From that question, what I understand is that I'm required to get this area. If it is the area to the left of, first and foremost, I know 1.23 is to the right of 0. Oh, sorry. That should be 1.23. 0 is somewhere towards the middle. So I know 1.23 is to the right of 0. And now I'm required to get the area to the left of 1.23. So I need to find the shaded area. I need to find the shaded area. This is easy because we just go to the standard normal. And you know, this shaded area starts from -infinity up to z-score value 1.23. So now, going to the standard normal tables, if you look at the bottom of that table, you can see the standard normal curve there and the shaded black part. The shaded part gives us the area, and it is made up of the values which are inside the table. Now we want the area to the left of 1.23. So to the left or below x, I look for 1.2. I can see 1.2. If I move towards the right, the first area that I see there is 0.885. But that is an area for 1.20. The next one, for 1.21, I see 0.887. But we want the one for 1.23. So at the intersection of 1.2 and 3 at the top, I can see 0.891. 0.891. So my answer for that example is 0.891. So the area to the right, sorry, to the left of z-score value 1.23 is 0.891. Okay, now let us look for the next example, the area to the right of 0.76 to the right of 0.76. So again, 0.76 is to the right of 0. That one we know, because positive values are to the right of 0. Now we want the area to the right of. So I'm shading the required area. We want the area to the right of. So we can do this in a number of ways. I will suggest one way. We know that the total area under the curve is 1, and we can easily get the area from minus infinity up to 0.76. So if I take 1 and subtract the area represented by z-score value 0.76, it will give me the area to the right. So this will just be 1 minus. I go to the tables, 0.76. Now we are becoming experts. At 0.7, there is 0.75. Maybe I can increase the size a little. Yeah. At 0.70, there is 0.758. We want 0.76. 0.76. So at 0.7 and 6 at the top, I can see 0.776. I can see 0.776. So it will be that minus 0.776. So it means that the unshaded area is the one which is 0.776. So to get the shaded area, it is just 1 minus 0.776, which is 0.224. 0.224. We're just trying to learn how to read the tables. We are trying to learn how to read the tables. We continue. Now, okay. I'm very good at doing this, at giving you something to think about. So with those examples I've done, now I will want you to get the area under z-score value minus 0.68, the area covered by the z-score value minus 0.68, and z-score value z-score value 1.82. So you will look for the area enclosed by those two z-score values. You will look for the area enclosed by those two z-score values, and in the next class you can remind me to give you the answer for that one, because it is very, very important that you understand this concept. So please remind me in the next class I give you that answer. It's very, very important for you to understand this concept. Now, we are still looking at how to get We are still looking at how to utilize the standard normal. Our next example is different. In the next example, find the z-score value. Find the z-score value having an area of 0.04 to the left. Find the z-score value having an area of 0.04 to the left. How does that look diagrammatically? How does that look diagrammatically? Somebody is asking us to find the z-score value which has an area of 0.04. So this area is 0.04. The area is to the left. Obviously, this z-score value must be negative. It must be negative because if 0 is here, you know that from 0 to the left, that area should be 0.5. From 0 to the right, the area should be another 0.5 to make an area of 1. So now, if the area to the left is 0.04, 0.04 is less than 0.5. So this z-score value here must be negative. It must be negative. So we want to find the value of that z-score value. I can see a red signal. It has gone. Okay. We want to find this z-score value. Now, I know we can all start thinking of different ways of tackling this question. I can suggest one method. Because the standard normal is symmetrical, then there must be an area to the right which is also 0.04. 0.04. There must be an area to the right which has a magnitude of 0.04. And so there is a particular z-score value here. And the z-score value that we are looking for, allow me to call this Z1. The z-score value we are looking for must be negative Z1. If I call it Z1, because the standard normal is symmetrical. So if I can get Z1, then my answer will just be the negative of Z1. Now, if the area to the right is 0.04, then obviously the area to the left is 0.96. It is 0.96. And we can easily identify from the tables the z-score value, which is Z1. We can look for the value of Z1 using this 0.96. Let me open my table. And you see, now we are looking for the area. So we go into the table and try to identify the z-score values from the left and the top. So going to our table, we need to look for 0.96. 0.96. I can see 0.959. Yeah, I can see 0.960. I can see 0.960. it is on the left of 0.960, there is 1.7. 1.7. Okay, and then if I look at 0.960 again, at the top there is 5. There is 5. So I know that that Z1 should be equal to 1.75. Z1 should be equal to 1.75. It should be equal to 1.75. But we were looking for minus Z. Minus Z. So this Z1 we have obtained, there is another one with the same magnitude but negative. Negative 1.5. And this is what we are looking for. So the Z-score value of an area of 0.04 to the left, the Z-score value of an area of 0.04 to the left is none other than minus 1.75. So there are some good exercises there on the same, which I will also send to your class reps, then they will forward to you. Okay, okay, so that is that about the standard normal distribution. That is it about the standard normal distribution. When I send the questions, you will be able to practice more to enhance your understanding. Now, we continue. Now, we have another distribution, which is known as the students' T distribution. Students' T distribution. In short, it is usually called T distribution. It is just called the T distribution. So what do you want to say about the T distribution? We want to say that it is used in performing, the T distribution is used in performing inferences. It's used in performing inferences for a population mean, for a population mean, for a population mean when the population being sampled, when the population being sampled is normally distributed, but the population variance, is unknown. But the population variance is unknown. So how does this student T distribution look like? How does it look like? Looking for it. How does it look like? Okay, there it is. Let me share my screen. So I'm sharing. I give it a bit of time so that everybody can see. So this is how the student's T distribution looks like. I know you can see three curves. Now, I need to explain. The student's T distribution has the general shape of a standard normal distribution, but it depends on the degrees of freedom. So we have many different student T distribution depending on the degrees of freedom, where the degrees of freedom are related to the size. So you find that if you have 1 degree of freedom, then the T distribution becomes more flat. It tends to be flat if it has only 1 degree of freedom. If it has 6 degrees of freedom, it becomes a little bit more steep. It tends towards the standard normal distribution. If the sample size is very large, you end up with the standard normal distribution. So the properties that we need to note about the T distribution are that 1, the total area under the curve is equal to 1. The total area under the curve is equal to 1. And secondly, it is also symmetric about 0. So actually, the two properties are the same as those for the standard normal. The only difference depends on the shape of the T distribution, and that is determined by the degrees of freedom. Now, we need to speak a different language as we go deeper. Now, we shall talk in terms of T alpha. T alpha. So when I say T alpha, what will I be referring to? T alpha denotes the T value. T alpha denotes the T value having area alpha to its right. T alpha denotes the T value having area alpha to its right. What do I mean by that? So this is my T distribution. It just looks like the normal, only that the degrees of freedom determine the steepness. So if I'm looking for a T alpha value here, T alpha value, just the same way that I was saying that let's look for Z1. Z1. Now, if we're looking for T alpha value, it means that this area to the right has a value of alpha. The size of this area is alpha. The area is of size alpha. So when we talk about T alpha, we're talking about the area to the right having a magnitude of alpha. All right, so let's do this. A few examples. We see whether we know how to read the T table. We want to find this. What is the value of T 0.03 with What is the value of T 0.05 with 13 degrees of freedom? What is the value of this? Let us go to our T tables. Please don't look at the standard normal. Now we need to go to our tables. Let me also open mine. T 0.05 with 13 degrees of freedom. I share my screen. Okay, there it is. T 0.05. Okay, sorry. Now, first and foremost, I can see that it has 13 degrees of freedom. So I need to look at 13 degrees of freedom. I can see 13. Then the level or the alpha value is 0.05. So I have identified where 13 is. Now I need to look for T 0.05. If I start from the left, at 13, I see 1.350. At the top of that is T 0.10. I move to the right again, I see 1.771. At the top of that is T 0.05. So actually, the value of T 0.05 with 13 degrees of freedom is equal to, the value is 1.771. Let me write that, 1.771. Okay, what about T 0.01 with 24 degrees of freedom? With 24 degrees of freedom. Going to our tables. First, we identify where 24 is. So let me minimize. So I can see 24. From the left, the first value I see is 1.318. At the top, T0.10. I see 1.711. At the top, T0.05. Let us move on up to 2.492. 2.492. At the top of that, we have T 0.01. So this is the value we are looking for. T 0.01 with 24 degrees of freedom is equal to 2.492. 2.492. Now, let's do something more interesting. So, what is T 0.975 with 5 degrees of freedom? T 0.975 with 5 degrees of freedom. Remember, T alpha means alpha area to the right. It means alpha, area to the right. So it means that our diagram should look like that. T 0.975. So the area which has a magnitude of 0.975 is this area to the right, is this area to the right. And now we want to find the value. We want to find the value. So remember that the T distribution is symmetrical. So it just means that there is it means that the red area, the red one, has a magnitude of 0.025. I'm just subtracting from 1. It has a magnitude of 0.025. And the T distribution is symmetrical. So if we get the T value such that the area I have demarcated is 0.025. Once we get that value, then we shall just put a negative on the value, a negative sign, because the T distribution is symmetrical. So how many degrees of freedom was that? It is 5. And then we need to look for T 0.025 with 5 degrees of freedom. So I'm back at the table looking at 5 from the left. I'm moving from the left. So we need the point at which we have T 0.025, and I can see that with 5 degrees of freedom and T 0.025 at the top, the value at the intersection is 2.571. 2.571. So it is 2.571. But this is for an area of 0.025 to the right. What were we looking for? We were looking for T 0.975 with 5 degrees of freedom. So the value of that will be minus 2.571. That is the value. So that is how we can read T values, and obviously I will send a number of questions for your practice. We continue. So we have looked at the standard normal. We have looked at the T distribution. Now, the third distribution that we shall use for inferential statistics is known as the, is the chi-square chi-square distribution, chi-square distribution. In short, we usually just say chi. This is how we denote. So that figure, that symbol is known as chi. So we talk about chi. We can say it is chi distributed, something like that. So when do we use this chi-square distribution? It is used to perform hypothesis tests. It is used to perform hypothesis tests for the standard deviation, of anomaly distributed random variable. Used to perform hypothesis tests for the standard deviation of anomaly distributed random variable. How does okay, there's a question. Somebody's asking me a very a question which I think is for engineers, and yet I'm not an engineer. Is degrees of freedom having the same definition as in structures? I think there is a unit you do for structures. Odhiambo, is that structures you're referring to? Is it in engineering? Because if it is in engineering, I really don't know. I'm not an engineer. For us, degrees of freedom, usually they are, yeah. So degrees of freedom are usually the number of independent observations, which, when you know them, you can determine the final one. Let's say you have a sample of size 20. So the degrees of freedom are 19. Why? Because if you have 19 data sets, or the values, if you have 19 values, you can determine the last one. So this is what we mean in degrees of freedom when we talk about degrees of freedom in statistics. All right. So for the chi distribution, usually it is right skewed. Let me just draw how it looks like. So our chi looks like this. When I say, let me write that, right skewed, because some people usually think in terms of stew. I'm saying that it is right skewed. What do I mean by being right skewed? It has a tail on the right side. This is what we mean by being right skewed. So you can see most of the values are concentrated more on the left part of the curve. So this is right skewed. It is usually right skewed. The properties, again, two important properties. The first one, the total area is equal to 1. The first one, the total area is equal to 1. The second property, it starts at 0. It starts at 0 and extends indefinitely to the right. Extends indefinitely to the right. Now, if I just in the same manner that I talked about T alpha, what do I mean when I say chi alpha? Chi alpha with n degrees of freedom. What do I mean? This is n, which is the sample size. What do I mean by chi alpha with n degrees of freedom? What I mean is that alpha is the area to the right. Alpha is the area to the right. Remember also T alpha, we said that alpha is the area to the right. And very soon we shall start talking about Z alpha. Okay, Majestic has answered what degrees of freedom mean in structures. It's the direction a node is allowed to rotate or move in. Okay, so I hope Odhiambo is answered. Okay, so I was saying that chi alpha with n degrees of freedom just is it refers to alpha area to the right. For example, let's look at a few examples. We just see how to read the chi-square table, not equation, example. Example. So let's get the value of chi what? 0.025 with how many degrees of freedom? With 12 degrees of freedom. So for us, it is the degrees of freedom. We usually obtain them from the sample size. So let me open my table 2. Chi-square tables. Okay. So I'm presenting my screen. Okay, so there we have the chi distribution. We need chi 0.025 with 12 degrees of freedom. So first I will look for 12 on the left side. First I will look for 12. Then I need to look for an intersection with 0.025. It is on the extreme. Why can't I look for 12 from the right side? 12 from the right side, 0.005. Now I'm moving towards the left, 0.01. Then I can see 0.025. And there I can see what's 23.337, the intersection of an alpha value of 0.025 and 12 degrees of freedom, 23.337. 23.337. Okay, now let's look for chi 0.95. Chi 0.95 with 7 degrees of freedom. Now, just to make it a little bit more clear, let me go back to the previous question, the previous example, and I try to show the region that we were looking for. So for that one, we were looking for chi 0.025. So maybe chi 0.025 to 5 with 12 degrees of freedom is equal to 23.337. Remember, it is the area to the right. So this area here is 0.025. What about this one for chi 0.95? So the area we are talking about is 0.95 is large. So this is the area we are talking about, the large area. So we need to read that value from the tables. From the tables, chi 0.95 with 7 degrees of freedom. So looking at 7 from the left, and I move towards the right, 0.95. I can see 2.167 with 7 degrees of freedom, 2.167 from the left. The intersection of 7 and 0.95 is 2.167. 2.167. So it looks like reading the chi-square values are very, very easy. Reading those values are very, very easy. Now, let us go to the next one. The last one, actually, we were just looking at 4 different distributions: standard, normal, T distribution, chi-square distribution, and F distribution. So even the F distribution behaves like the chi-square distribution. It also behaves very much like the chi-square, only that it has 2 degrees of freedom. For example, we can have degrees of freedom equal to 9 and 50. So we have a degree of freedom from the numerator, the first one, and the second one is obtained from the denominator. So the first degree of freedom is obtained from the numerator, the second one is obtained from the denominator. And we will see that in the following examples. The properties, again, it also has two important properties. Of course, the total area is equal to 1. Okay, there is a comment. Okay, so only standard values will be asked. You will not be required to extrapolate. We will, when we set the question, we set it in such a way that you can read the value from the table. Okay, so you don't need to extrapolate. Even there is no time to do that in the exam. You just want to read, answer, and move to the next question. Okay, so I was saying that it also has two important properties. The total area is under the curve is equal to 1, and it starts from 0 and goes on indefinitely. It starts from 0 and goes on indefinitely. Now, let us read this. F 0. Remember also this one, it's a matter of the area, the alpha value representing the area to the right, F 0.05 with 4 and 12 degrees of freedom. 4 and 12 degrees of freedom. What is the value of this? As you open your table, I also open mine. F what? F.05. Remember the F's. I need to rotate my table as I present my screen. Let me rotate it. Okay. So it is F 0.05. I have opened the correct table, F.05 with 4 and 12 degrees of freedom. So I said the first value is the numerator. The first value is the one on the first row. We read it from the first row. The second value is read downwards on the left. So if we want F.05 with 4 and 12 degrees of freedom, 4 and 12. So I just go, first of all, I read 4 and I move downwards until what I have on the left is 12. Until what I have on the left is 12. So at the intersection of 4 and 12, 12 is on the left. I can see 3.2592. 3.2592. 92. And remember that this F.05, it's also referring to an area of 0.05. It's referring to an area of 0.05 to the left. So this area here is 0.05 to the right, not to the left. 0.05 to the right, and the degrees of freedom are 4 and 12. 4 and 12. The degrees of freedom are 4 and 12. Note something. If you looked at the tables that I gave you, there was f.05, f.0, f.01, 0.005, 0.05, 0.025. I did not give you tables for f.95 and so on. So what happens if we need to calculate something like f.95 with 60 and 80, 60 and 8 degrees of freedom? How are we going to do this one? This is why I'm saying note that f 1 minus alpha with m and n degrees of freedom is given by 1 over f alpha with n and m degrees of freedom. So a few values, the degrees of freedom are interchanged and you get the inverse. And so I will want you to obtain this value during your spare time. Try to get f.95 with 60 and 8 degrees of freedom using this property that I have given. And I can give you the solution for that one in the next class that we shall have on Thursday. In the next class that we shall have on Thursday. Otherwise, I will send very many questions to your class reps for practice. I will send many questions to your class reps for practice.